Hi, this is Dr. Brothers, and I'm going to go over a lecture on circuit protection and design for safety. This was originally created by Aaron Lanterman and Professor Kinney, Steve Kinney. So, why do we need to protect the circuit? So, first thing is for safety. We don't want it to explode. We don't want to release the magic smoke. The magic smoke can hurt people. Economics. It's a 50-cent fuse versus a PCB assembly, which is $500. That's a very cheap estimate. A lot of the boards that I deal with are several $1,000 real-time FPGA boards. So fusing is very, very easily. Reliability. So if you get over voltage or current or power over any of those, it shortens the life of a product, even if it doesn't blow it out. The more times you heat something up and then cool it off, it's going to lower the life of your product. So it's just good practice. So look at a 2.1 millimeter DC barrel jacket. And I've actually had this happen before personally. These connectors are the same, and you need to watch the polarity of them. So most devices like hard drives use positive tip standard, but there's this negative tip standard. It's the same plug, but it reverses the polarity, and that will blow out your electronics. So what do we do? How do we make sure something as simple as polarity? Diode clamps are the best way to limit overvoltage conditions. So D1 and D2, here are the two diodes. D1 and D2. These are the limiting diodes, and you can see that the VCC and the negative VEE, as long as the voltage in is within these bounds, it's good. So if we reverse polarity and flip it, it's going to be outside of the bounds, and it's going to either flow to the VCC or flow in this direction and sink current into it. So we can use these diodes to protect the downstream circuit by diverting that voltage, that current, to another location. So this is from MOFS, and that was, I'm going to look at my other slide. Hold on just a second. This is, where was it? Music from Outer Space is the name of it. And I want to give you a broader perspective of what this is. Let me pull it over from my other screen. And so this is the circuit that we're looking at. There are quite a few op amps in it. So music from outer space. This example is doing a 1 volt per octave voltage controlled oscillator. So this is a way of analog generating a tone. Very straightforward. If you have not looked into any of these, please read through. Like, this page is really good. And it shows the circuits for making a voltage-controlled oscillator. And for this one specifically, the op-amp that it's looking at right here is the triangle output, the triangle wave output coming off of this op-amp. And the question that is brought up is what happens, hold on just a second, technical difficulties. So the question that is brought up, what happens if this op-amp rails at the full voltage, which this is a 14 volt or 15 volt, so coming through it, it has some loss, probably 14 volt on the output. What's the power dissipated through this resistor? If you look at that, power is equal to V squared over R with a 1K. That's approximately a 0.2 watt or 200 milliwatt of power that's going to sink out of that resistor. If we go to the data sheet for this particular product, this op-amp, ours is the, let's double check, the TL074. The TL074 is this top line on the total power dissipation versus free air temperature before you burn out something. And here's 200 milliwatts. So we need it to run about negative 30 degrees C in order to keep that op-amp from burning out if we short circuit the output. So what we can do there is make sure that this resistor pops before the op amp. And so we can save the upstream electronics if we intentionally select a resistor with a low voltage output. This could also be a fuse. There's a lot of ways that we could guarantee that it protects it in case somebody connects a ground, that tri-stated output connection on the exterior of this circuit. So there's a variety of shapes, sizes, current voltage ratings. Here are some of the examples of different fuses. You've probably seen these around in electronics. Fuse specs, you can have fast blow, slow blow, and so there is a curve, the current in amps and the time in seconds as the relation, and how long it takes blow. So for 100% of its rating, it's going to take on a slow approximately 4 hours, or 4 hours minimum. And then if you get to 200% of the rating, it's only a couple of seconds. And then 400 to 1,000% you can see on the fast blow, it's milliseconds. So voltage rating, the maximum voltage with which the fuse will not arc, break down after blowing. So here are some more examples of some slow and fast blow fuses given their current ratings. So these are relating current to time. And so we can look at how long, and this is a log scale on the time, and you can see how the curves are going to go off. What's literally happening, it is overheating the element that is inside the fuse. So if it just goes over for just a real short amount of time, it won't blow it. But if it goes real fast or for a long duration of time, it will blow. Okay? So tips on fuse design: use fast blow for most of our electronic applications. They're not completely reliable for high-speed electronics, too slow. Use in conjunction with electronic protection circuits. So use this in conjunction with like the diode clamps and that type of thing. Use slow blow for motors, lighting, or anything with a significant reoccurring surge. So motors, when they kick on, they pull that large amount of current right at the beginning to overcome the coefficient of friction and start moving. And so it's very common for them to pull a whole bunch and then go to a higher efficiency state as they come up to speed. So you don't want the motor to blow out your fuse right when it kicks on. So you usually derate the voltage by 2x, meaning that whatever the voltage is that you expect to run at, say 120 volt AC, which is our common household electrical wiring here, you want to basically double that and pull a 250 volt fuse, so derating. Locate in easily accessible locations on chassis. In AC power line, you can couple these into the AC power line on the PCB so you can access it without removing the PCB. Keep plenty of spare fuses on hand when prototyping. You're going to hook these up in the lab. Make sure you're ready to pop them and replace them. So there are also resettable thermal fuses, and so it goes into a tripped state, and then it can be reset by squeezing it back together, or power cycling. Yeah, I'm sorry, these aren't the physical ones with the push button. These, you'll just power cycle it and it will rebuild its state. Circuit breakers. These you'll push the button on. So these are magnetically activated switches. A lot of this is you've seen in your household wiring, such as the square D breaker on the top right. Here are the push button breakers, and then there are some also fuses, or these are trip breakers also. So 10 to 1,000 times the cost of a fuse, because a fuse, you just burn it out and you replace it. These pop and you hit the button to reset it. Design for safety. Circuit protection does not protect you. The reason we do circuit protection is to try to protect our electronics. When you are doing testing, when you're doing prototyping, you need to be aware of where the high voltage is at, and you need to have it covered in a safe manner. Use terminal strips with the appropriate mechanical covering so nobody can accidentally drop a tool on the high voltage AC connectors. Do what you can to protect yourself in the lab following the safety guidelines. This is to protect your circuit. Shock hazard. Accidental shorts and shocks from alternative ground return. So in this case, it's going around a circuit. It has an alternating input, and the circuit breaker is here, but we're going to divert it through our body and go down. So in this, severe, here's the amps. Severe burns, stop breathing, death is between 0.1 and 0.2 amps. Does anybody know what a household breaker is usually at? 15 to 20 amps. So be very careful with this. This is not meant to protect you. This is meant to pop if the electrical wiring of your house is getting too high. So circuit breakers and fuses will not protect you against shocks. AC grounding and isolation. For this semester of the capstone design project, everybody is pretty much going to bring in 120 volts. So you need to think about how you're going to isolate and ground. So if you're using a metal chassis, you need to ground the chassis as is shown in the red circle. And then there are the coupling capacitors that are going between the hot and the neutral to bring that also to ground so that those will short out if needed. And then this is indicating a transformer on the primary and secondary side. Those also need to be coupled into the ground plane. High voltage isolation in control signals. So we have a relay. A relay takes quite a bit of power to pull it together. Relays control, digital controls, high voltage current, and it's low speed. So in this, there is an air gap, and it pulls together, and it turns on the high voltage. So we're using a low voltage digital signal to connect the contacts for the high voltage. So this is a very good, safe device. These are a little bit expensive to use in a circuit. So you wouldn't want to use these unless you're doing some type of a remote control or you're turning on a high power motor or something like that. Opto isolators, analog and digital signals, high voltage, low current, high speed. These are really nice when you are trying to go across the medium and make sure. So a lot of times you might want to use one of these if you've got a cable connecting over a long distance and it's carrying data information. These two remote sites might have different ground planes because if they're on different ground circuits in the building. One of the things that we would do oftentimes when I was out on the government test ranges in a previous career, it was very dry soil, and we would drive in grounding rods in order to ground our site. But because the soil was so arid and so dry, we could have massive voltage potentials from one grounded location to another grounded location. And then if we ran a long cable between those two sites and just connected the grounds together, there was a big current that would flow through the ground wire. This is how you can isolate it. You can isolate those communication signals using opto isolators in order to keep everything from feeding back, such as different ground planes. When you bring in the higher voltage like 120 volt AC cables into your box, they need to be properly strain relieved. So these are some examples of how you can physically constrain the cable so it's not going to get pulled out of your box, and the terminal lugs might come loose and short against the box. So physical strain relief is very important, as well as circuit protections. Solid versus stranded wire. Solid wire can carry a high current, but it has low flexibility. It's cheap, it's durable, used for long runs of fixed wiring. For instance, the wiring that's ran inside the walls of every building, this is a solid strand. Stranded, usually we use those for a lower current situation. It has a lot more flexibility. So for instance, if you want to use a mouse cable that's going to be moved around a lot, you want to use stranded cable because those individual strands allow it to flex more. So, but more strands mean it's going to cost more because they have to extrude all those strands and mix it and twist them together. Use when cords will be repeatedly moved. So example, like mouse cords, the power cords coming into your computer, a lot of those will be stranded cables. So here is a good practice design example. This is the Apple iPhone charger. So we're coming in with a USB cable, or we're coming in with 120 volts. And then we have a USB cable and a PCB connected to that. So this is 100 to 240 volts AC, so it will support both the United States and the European standards. The output's a 5 volt DC at 1 amp, 5 watts total output. Switching frequency is 70 kilohertz. So this has two PCBs, one on the top, one on the bottom. They're sandwiched together. So we're going to have a primary voltage and a secondary voltage that are connected across, and you can see some of the big caps that are used in this design. So here's the high side and the low side on this circuit. And on the very input side, we can see we have R1, which is used as a fuse resistor. So that one will pop out first if we start to get a large feedback on this path. So then we also have, let's see, that's the only thing really interesting on this slide. If we look at the top side and the bottom side, we see all sorts of goodness in here. We have some bridge diodes on this side. We have a fusible resistor. So here's a resistor that's meant to blow out if it needs to. Here's some more clamp diodes. And then transformer resistance cap. Okay. Auxiliary power components. And then on this red diagram, we have more clamp capacitors and diodes. Current sense resistor. So the current sense resistor is used to make sure that we're not going over current. Here's some more bridge diodes. So all types of great protection on this circuit with a lot of these bridge diodes, as you can see, in a lot of these places. In order, well, these are rectifying diodes. Yeah, I should have looked at that circuit a little bit more before the lecture. But the bridge diodes are pulling it down and making sure that we don't go over. Here we go. Over current. Here's the thermal protection. So it's going to monitor and turn it off if it gets too high. It's going to short that out so that the voltage goes through that path instead of actually powering the circuit. Here's the cost of it. This whole thing, $5, $466. So there was a lot of energy put into this at the beginning in order to make sure it's safe, make sure it had all the protections that it needed. But when they actually got down to a per part cost, it wasn't that bad. So in summary, pay attention to circuit protection and safety, or get burned, shocked, or both. Circuit protection, fuses, cheap and easy, resettable fuses and circuit breakers, more expensive, but don't require replacement. Over voltage protection, inrush current protection. Think about all of these things in your design. Design for safety, AC isolation and grounding. This is going to be very important when you go to design your circuits, that the AC is coming in and getting grounded off properly, and then it's getting transformed over to your DC as required. So there are a lot of good AC to DC converters that we have in stock, We want to use those and install them properly. Signal isolation, mechanical considerations, and then there's other considerations such as fire, optical, radiation. So a lot of those, the requirements that we've put into this design include making sure that we have the internal temperature of the box held at a constant throughout the design. All right, I'm not going to go through the appendix on this PowerPoint, but if you would like to go through this appendix, there is a lot of detail about inrush protection, over voltage protection, cable insulations, fire, RF, optical, and this was put together by Dr. Lanterman, so more guitar pedal details just for fun. So feel free to look through this and see how you can put more protection in your circuits. But think about this at the beginning to make sure that everything you do is safe and effective. All right. Have a wonderful day.